Welcome back. So, we had been discussing about RF power transistor, introduced the basic concepts there. I told you in today's lecture we shall discuss a very important figure of merit for RF transistor. It's called Johnson figure of merit, and we'll see that what are the materials and devices with a better Johnson figure of merit and how it is derived, and from there we'll conclude RF transistors and we'll move to things like memory or logic devices where we use transistors. Remember, we are discussing about the applications of transistor in some broad areas, primarily power switching, RF power amplification, memory and logic. There are many other applications also, but these are the main 4 applications that we are talking about here. Okay, so let's continue with the discussion on the RF transistor, and we'll come to the whiteboard to discuss about Johnson figure of merit. Johnson figure of merit, and Johnson figure of merit is very important for RF devices. It tells you how good an RF device is. So, if you think of any transistor, you are thinking of any transistor, say this is gate and this is drain, by the way, if this is gate and this is drain, this region actually in the channel, this is the channel probably, this is called the drift region, okay, and your voltage is typically blocked in this drift region only. Okay, as you deplete the gate, the depletion extends sideways towards the drain, and so that blocks the voltage. So, this is the drift region that we talk about. The electron has to drift through this region. The material has a fundamental breakdown field, that is E critical, that is a fundamental property, we cannot do anything about it. If this is the maximum field that you can sustain, and this is the drift region, that the thickness of the drift region here is called as, say, L drift. This is the drift region that it has to go, maybe 1 micron, 10 micron, whatever you decide that. Okay, then the breakdown voltage that you are holding between this, the V breakdown, the breakdown voltage that you can actually have is given by the product of critical electric field times the drift region. Okay, this is your breakdown voltage. Fine. Now, in this drift region, the electrons have to transit. The electron will move across the drift region, right, through the channel and come out through the drain. So, there is a time taken by the electron to drift. What is the time taken by the electron to drift? The time the electron has to move from the gate to drain. There is a source here, but the electron, while injected from the source, it has to move from in the gate drain region, which is the most crucial region for blocking voltage. There is a time that is there, and this is typically given by the distance, the drift distance divided by the velocity with which they move, and the maximum velocity with which it can move is the velocity of saturation. Simple. So, this is the minimum time it will take to move there. Okay. Now, the current gain cutoff frequency, which is Ft, the speed, the current gain cutoff frequency, which is speed, is actually given by, this is the speed, okay, the fast is actually given by 1 by 2 pi times the time it takes to drift. You can say how much time the electron takes to drift is inversely proportional to speed. If it takes a longer time, the speed is low. If it takes a smaller time, the speed is fast. So, Ft is actually directly proportional to 1 by, you can say, the time taken to drift. Okay. Now, I will come again here. So, if I from here, if I put that, then Ft, if I use this expression here, then Ft is actually V set by L drift, right, and I can put L drift from here as VBR by ECR. So, I can say this is V set divided by VBR, right, into by the breakdown field. Okay. So, what I can do that is that what I can do that is I can write it better. I can say Ft into VBR is equal to V set into E critical. Now, this is actually the Johnson figure of merit. So, the frequency at which you can operate times the breakdown voltage is equal to saturation velocity of the electrons times the critical electric field. Now, the saturation velocity of electron is a fundamental material property, you cannot change that, right. Saturation velocity in silicon will be constant. Similarly, fundamentally the critical breakdown field also is a fundamental property, you cannot change, it is constant. So, in other words, the product of the saturation velocity and the critical electric field is a constant is a constant which you cannot change. So it means that your product of frequency at which you operate the device, I mean not operate, the maximum frequency that you can get in a device times the breakdown voltage, the maximum voltage at which you can operate the device, that product is going to be constant and is limited by the product of saturation velocity and the critical electric field, and this is called the Johnson figure of merit, right. You see, the critical electric field is fundamental property. So for example, in silicon it is around 300 kilovolt per centimeter, but the breakdown voltage is not fundamental. If you use a thicker silicon, you will block more. You can block 100 volt, you can block 1 kilovolt, whatever, few kilovolts. It depends on how thick you want to make the silicon, right. This is not a fundamental property. So the maximum voltage that you can get, the breakdown voltage you can get times the maximum speed you can get, that product is constant, okay, which means this is called the Johnson figure of merit, JFOM, and a higher Johnson figure of merit means that the transistor is better as an RF device. Because in RF device, why it is important? An RF device, you want the speed, of course the RF device has to work at speed, you want to work at 4 gigahertz, 8 gigahertz, 12 gigahertz, whatever. So you need speed, and also you need a higher output power, a higher RF output power. If you do not get higher output power, then there is no point. You need to get higher watts in the RF, and to get higher output power you need to actually have a higher breakdown voltage in the device. A higher breakdown voltage in the device means that your gate drain voltage can be high, and so you will be able to block larger voltage. It's not like a power switching device, but nevertheless you see, when you operate a power transistor as a in a C bands, for example in 4 to 8 gigahertz or whatever, 8 to 12 gigahertz, anything, you have something called VDD, that is your drain bias or the supply bias. That supply bias will decide how much output power you have. Typically the supply bias could be 28 volt, then you will get some power. You can also put the supply bias as 50 volt or 100 volt. In case of 50 volt supply power, your output RF power will be also more than in the case of 28, and so on. In 100 volt it will be even more. So you want to bias the device at a higher voltage. Not bias, matlab the supply, the VDD should be at a higher voltage so that you can get better RF output power. But to apply a higher voltage, you also breakdown needs to be high. For example, if your breakdown of the device is 100 volt, you cannot operate the device at 100 volt, you have to operate at less, like 50 volt or whatever, right. So you need to have a higher breakdown voltage, and also you need to have a higher speed. So those are two crucial parameters that trade off with each other. A higher breakdown voltage will lead to a smaller speed, and a higher speed will lead to a lower breakdown voltage. So you have to trade off between the two, and that is a very important thing that people tend to forget, but it's very important actually. So I'll show you a picture here. Okay, I'll draw a picture here. So what will happen actually is that I'll change the slide, and what you can do is that you can plot the breakdown voltage on the y axis. On the x axis I can plot the frequency. So suppose this is 10 gigahertz, this is in gigahertz, okay, and suppose this is 100 gigahertz, this is 1000 gigahertz, 1 terahertz. There is no transistor that will probably give a gain at 1 terahertz almost. Very very few indium phosphide is close to 1 terahertz. So you will have silicon that will probably go like this, right. Then there is indium phosphide, this is indium phosphide, this is silicon, then there is GaN. Okay, this is breakdown voltage, maybe 1 volt, 10 volt, whatever, 1000 volt, and so on. Okay, so I'm not drawing accurately, but if you draw accurately, you will see that if you want to get a frequency response of say 200 volt, 200 gigahertz cutoff. If you want to get a 200 gigahertz cutoff, this is not 200 gigahertz, sorry. This will probably be around 600-700 gigahertz in this case. Suppose you want to have a 200 gigahertz transistor, you want to operate at 200 gigahertz, the maximum operation frequency is 200 gigahertz, then only you will get a few volt, maybe you will get some 5 volt or so. That means at 200 gigahertz, if you want to get a cutoff at 200 gigahertz, your silicon transistor cannot have a breakdown more than 5 volt, which means your device has to be biased at like 2 volt or 1 volt, and that will your output power will be very very low. At the same time, in gallium nitride you can actually bias the device at much higher, because at even at 200 this thing you will get probably like 100 volt or so, okay, maybe 200 volt or 200 volt or something. That means at 200 gigahertz cutoff frequency you can still get a gallium nitride device that can be close to 100 volt, and you might be able to bias it higher, so you will get higher output power. So these devices are actually better than silicon in terms of Johnson figure of merit, in that for a same frequency you will get a higher breakdown voltage, okay. So dominant technologies, I told you, indium phosphide, gallium arsenide, they are used very widely in they may not be able to give the best of power, but they operate at very high frequency. So in India also, if you want to look up, for example, there is this company, a government actually company, it's called GATEC. It's situated in Hyderabad. You can Google up today, GATEC Hyderabad. Actually it's gallium arsenide enabling technology, something like that. It basically makes these gallium arsenide MMICs, or this monolithically integrated circuits, all the transistors, gallium arsenide, even they work on gallium nitrides. You'll see that they make these devices for strategic and other space applications. These are indigenous gallium arsenide, gallium nitride devices that are being made, and these are useful for RF applications, okay. So that is very important for RF applications. So now that there is a trade off in the RF devices in terms of breakdown and not on resistance but the frequency, okay. And this is also called, the Johnson figure of merit is also called power frequency trade off, or PF square trade off, okay. So that brings us to an end to the discussion on RF transistors, and the next we will move towards is memory devices. So what kind of memory devices use transistors and semiconductors? I am sure you probably know of many of the memory devices, definitely, but many of the details might be missing. Some of the important parameters of a memory device, okay. What are the target criteria in which you distinguish the memory devices, or you classify, or you rank the memory devices in terms of their performance and other things? One is called volatile versus non-volatile memory. Do you know what is a volatile and what is non-volatile memory? Whether you can erase the content versus whether you can, if it will eventually, whether this memory, the information will be there, or where the memory information that you store there will eventually go away. I'll come to that again later. One of the thing is called areal density. Areal density actually is of information. How many kilobytes or megabytes or gigabytes of data can you store per inch square of physical space? Like, I have a memory that is 1 inch by 1 inch something, pen drive, hard drive, whatever. How much memory can I store? Can I store 25 GB, or maybe I can store 1 GB only, or so on and so forth, okay. That's called areal density. You want a very high areal density device. Do you know what is the maximum areal density today? We'll come to that, okay. You want a very high areal density so that at very small location, very small size, you are able to store very large amount of information. That's called areal density. One of the important parameters, of course, is durability and lifetime. How long the device will work, what is the durability, how robust it is in a way. Another thing very important is speed of reading and writing. You have to read from the memory, you have to write to the memory, right. When you store information on the memory, it is writing, no, and when you retrieve it, it's called reading. With what speed can you do it? It cannot be like, you wait for many hours to write just to copy a single file. That doesn't happen. So the speed is very important. And of course everything else remaining same, what remains important is cost, which is what is the price per unit dollar. How many bits can you buy, or how many per unit dollar, how many bits are you storing, okay. These are very important things. So some of the common memory devices are, of course, SSDs, which are called solid state drives, which are very upcoming, and very solid state drives which are very widely used now, and also we call them flash drives, the same thing, okay. We call them flash drives. Flash drives are something like your USB thumb drives, the pen drives that you have, okay, the pen drives that you have or the memory cards in your camera and other things that you have. And of course the second one is there are many storage devices like DRAM, and DRAM is not for storage, by the way. This is for computer booting up, where you store the cache and all files, right. DRAM is not for storage per se, but it's for computer booting up, and so all this dynamic access resistant random access memory we call them. Then there are these magnetic memories, magnetic storage devices or magnetic memory devices, which are like the hard disk, the traditional hard disks that you have in your computer, that that plugged, the traditional hard disks that are inside the computer, many of the previous generation hard disks that you can connect with a plugged supply, right. Then other things are disks. Disks are like CDs and DVDs, which have become extinct already. Although we have seen their rise, but they have also become extinct. Out of these, there may be other one, SRAM and all. How many of them use transistor? Do you know? These do not use transistors. These do not use transistors. These also do not use transistors. Magnetic storage devices use magnetic materials and other fundamentals. It doesn't use transistors. Transistor is used for DRAM, for example, although it is not for storage. Okay, it's a memory device, not for storage exactly. It's for computer booting up and all. And solid state drives, flash drives, they also use transistors. Exactly, it's not a transistor, but it's a transistor structure. You will see that, and why it is called a flash memory, right? I told you we are talking about the different kinds of the technologies that are using the transistors. We don't have to go into the basics of magnetic storage and stuff like that, right? But there is something called, you can plot the areal density of, I told you areal density is the number of bits or bytes per square inch you can store. This is the areal density, and this is your year, right? So from 1990 all the way to 2020, right? So all the way till 2020. So your magnetic hard drive and your solid state drives have gone up steadily over these years, increasing in their areal density. So one of the curves is going like this, for example, right? One of the curves is going to, so this is your hard drive, for example. So the hard drive has gone from, like, this is at 1990, it was close to 1 maybe megabyte, 1 megabyte per inch square, or less than that probably at the area. And now eventually it has, this is a log scale, by the way, this is a log scale, it has gone up crazy high. So now you're talking about maybe few hundred gigabytes per square inch, few hundred 10 to the power 3 gigabytes per square inch. It's like almost 1000 gigabytes or 1 terabyte per square inch. And then you have, of course, solid state drives that have decreased, that was going at very slow pace, but suddenly it has caught up, and now it's almost overtaking hard drive. Solid state drives or flash drives are now starting to overtake the magnetic hard drive storage in terms of areal density, as to how many bytes or bits you can store per square inch. That is a crazy number, right? You might want to zoom it and see. If you want to zoom it and see, then in 2013, and this is 2025, for example, we'll have data till around 2017. Your magnetic hard drive is going like this, right? But your solid state drive is going crazy. Already it is exceeding the magnetic drive, and it is supposed to go towards even high. Okay, and what is this is the areal density. So this point, for example, this point where they are crossing is around 1 terabyte per inch square. That means in a 1 square inch by 1 inch area, you are able to store 1 terabyte of data. So this is around 2014 2015 data, a couple of years back. So your solid state drives are now actually able to store more than your magnetic hard drives in terms of areal density. It has crossed up to, I think, 1.7 terabyte per inch square of data it can store, right? Well, magnetic memory devices will grow, but it will not grow as fast as your solid state hard drives and memory devices, right? So now this is about the basic idea that this is the thing. But how does these devices work? As I told you, you have flash memory devices, and then you have DRAM devices that are used in that are made from semiconductor your transistor technologies, for example. So flash is used in, as I told you, like pen drives and USB drives and so on, and DRAM is the main memory in PCs and workstations, helps in computer booting up and other things. You have the read write sort of font, right? So I'll come to the working of the flash, which is more important and more uprising in these days. So flash is a very dominant technology, and it's made of actually a silicon MOSFET sort of a transistor, but slightly different architecture. When I say slightly different architecture, what I mean is that you actually have, you will see that the structure is very similar. You actually have an N plus source, okay, and you actually have an N plus drain, which is just like your silicon MOSFET that you have studied, or MOS capacitor that you have studied, and it's a p-type body which is very similar, right. And then of course you are making a contact here to the ground. Over here I am talking about a flash, how a flash works actually. Okay, the simple architecture how a flash work. You are not biasing the drain, you are actually pumping drain current here, because there is a line that is called the bit line. Okay, that is the bit line that will read and write the data. That is a bit line that will pump some current, that will get some current out of this drain. Now you have your oxide here, you have an oxide here, right, and then you have a metal gate, you have a metal gate here. Now you might say this is just like the silicon MOS capacitor MOSFET, right. I will come to the difference. It's your metal gate here, but the metal gate actually is floating, which is very strange, right. On top of that there is also another oxide, which is strange, and then on top of that you have another metal gate, right. This is your another metal gate, this is also metal gate, but this is isolated metal, and this is this metal gate, this metal gate is connected to the word line, you know, word line and bit line. This is the bit rise and this is the word lighting there, right. So this is connected to the word line. This is your, actually we call this top metal as the control gate, because that's where you are applying the word line, right, control gate, and that is connected to the word line. But this over here, sandwich between two oxide layer, is actually called floating gate. Floating gate. The floating gate actually is floating, so it's actually not doing anything. I'll come to that. And this oxide in the lower part, this oxide is actually very thin, it's called tunnel oxide. Carriers will tunnel through this oxide actually. So how does it work now actually? The way it works is that you are charging and discharging this capacitance. Okay, you are discharging and charging this capacitance with a field resistor tunneling. You will actually get carrier tunneling across this. Okay, this is the thin oxide. You are able to tunnel through the carrier through the thin oxide, and that tunneling happens very fast. Your reading and writing, or your charging and discharging of this capacitance, will depend on this tunneling current that is there. I will come to that quickly. And this tunneling current happens, this charging discharging happens very quickly in a flash. That is why it is called flash memory. It's happening like a flash. Okay. The way it works is that you know, if in the control gate, if you induce a positive charge, then you know you will eventually have some negative charges here, right. So on the floating gate, this is the floating gate, right, this is the floating gate. On the floating gate you will have no net charge, only polarization charges induced by the charge on the top gate. Okay, and you will have a reduction in the electron charge in the channel due to charge. If you have charge, if you are inducing charge on the in the floating gate, if you induce charge on the floating gate, then you will reduce the charge on the, by charge conservation principle, you will reduce the charge in the channel, you will reduce the charge in the channel, right. So essentially what you are trying to do is that by this word line you are putting this charge or taking the charge away from the control gate, you are able to change the charge state of the channel by changing the charge state of the floating gate here. This is the floating gate here, and extra charge stored can be tunneled through this oxide. How, for that you have to draw the band diagram, right. So I will quickly draw the band diagram here that you will see. So in equilibrium I will draw the band diagram. Okay, so this is your Fermi level, this is the Fermi level, and you have your floating gate in between. So this is your oxide, okay, and you have your conduction band and you have your valence band. This is your p type substrate, this is your floating gate, so I will call it Fg, it's your Fc. Now when you are writing on this device, what happens is that you are applying a negative, this is the main gate, control gate, you will apply a negative voltage on the gate. So what will happen is that your device, your band diagram will look like this. Okay, your band diagram will look like this. So you are applying a negative voltage here, minus VGS, and your bands will bend like this. So the bands will bend like that. So what will happen is that you will be able to tunnel inject an electron, you will tunnel inject an electron and it will form in the level here. Okay, you will tunnel inject an electron here, and that's called the write operation, right? And when you store, you remove the charge, it will store. Basically what will happen is that you will have a when you remove that bias, you will be able to store the electron will be stored here. Okay, the electron will be stored here. Okay, the electron will be stored here, and when you want to erase the thing, then you apply opposite polarity on the bias on the gate. So what will happen is that you will have something like that, then this will have a field assisted tunneling, because the field will become like that, the bands will go like that. This is EC, this is EV. You apply the opposite polarity thing. This is a field, very thin field, and as a field assisted tunneling will happen. Field assisted tunneling is also called Fowler-Nordheim tunneling. Okay, this electron will be able to tunnel out. Once the electron tunnels out, the information stored is lost, and that's called erasing. So this movement of electron by tunneling here inside, and then going outside here by erasing, this tunneling in and out of the electron with the floating gate and the tunnel oxide, it happens in a flash very quickly, and that's how you read and erase, okay, data. You can read and erase data. Okay, you can read and erase data. So this electron that you store, unless you apply a field here, it will not be able to tunnel out itself, because the tunneling oxide say it cannot tunnel out unless you apply a field. So this electron will remain there as long as you want, in a way. Okay, but again there is a slight discharge might happen, but that's a different field of study altogether. So so this is the basic operation principle of flash memory, and it uses a p type silicon or n type, this NP silicon, and it is very fast, and you can store information very quickly. You can read and write very fast. You can have very dense information, because your transistor MOSFET fabrication techniques are very advanced. You can write a lot of these transistors in a very small area. So that is the reason why you can have very high density of information that is stored within within a small area. Okay, unlike the magnetic hard drive memory, magnetic hard drive memories that you have are actually not transistor based. Those are magnetic material based. You have some other mechanisms to read and write memory there. We are not going to talk about that. Okay, but this is a main application of a semiconductor memory, the flash memory, which uses a floating gate, a tunnel oxide, to essentially tunnel the electron in and out to read and write the data. Okay, and this is unique in application. You cannot do it in non semiconductor based devices very well. So this is a broad application of a transistor as a memory devices. So what remains now is transistor as high speed logic. I have already discussed the transistors that are useful for high speed logic, which is silicon MOSFET. That we will discuss in the next class perhaps. So we will end the class today here. We have discussed the final part of RF transistors, Johnson figure of merit, and also I told you about the power frequency, the limit that you have and different materials that you can use for superior performance, like indium phosphide, gallium nitride. Then we moved ahead and we went to this flash memory and the different kinds of memory technologies. I told you that flash memory is one of the very uprising and rapidly expanding memory device market. Silicon MOS structures with a floating gate in between the gate oxide and tunneling oxide enables this. You tunnel the electron in and out through the tunnel oxide, and that's how you read and write the data. It happens in a flash, like very quick. That's why it's called flash memory. So what remains now is probably a couple of more lectures to end this course module, fundamentals of semiconductor devices. So in the next lecture we'll quickly go through what is needed in a CMOS logic. You already know the MOSFET, MOS transistors. That is what basically CMOS logic is all about. I told you we'll quickly run through some of the techniques used in device fabrication. What are the practical or experimental techniques used in making the transistors, diodes, LEDs and so on. Maybe in the last lecture we will try to solve some of the question papers and some questions, semiconductor numericals and questions that are asked in some common exams like GATE or NET or something else, okay, to give you an idea of how semiconductor questions have to be attempted. Okay, so with that we will end the class here. Thank you for your time.